computer. So now it's recording. Now I need to click on the share screen, press this thing. So I guess that now I'm sharing is post, right? It's post. Bring your share. What happened there? Oh. Let's see if I don't understand. Stop share. And now hit share screen here and share. It's wrong. What's wrong with this thing?
There are some background noises. I think someone is not muted.
Oh. What is wrong? What?
It's better.
But I don't see the I don't see my screen. Do you see my screen?
No, we now we see your screen.
For reason I don't understand why they didn't show, now it shows. Okay, miracles of Zoom. Miracles of Zoom. Okay, so we are ready to start. Let me just close the door. And let us start. So more or less as I said, we finished talking about electrons and static disorder. And now we will go and talk about electron phonon kinetics. Well, in a metal/semiconductor, under numerous assumptions, simplifying assumptions. Of course, it's a very big subject. We will be able to cover only a small part of it. By the way, there is a book by Yeshua Levinson and Gantmacher called Scattering in, I forget where, but you can Google it. It's a very nice book. It's probably, so if you're interested in learning more about scattering electron phonon kinetics, you can always look into this book, and it discusses all these subjects much deeper than what we do. Okay. So what do we know about electrons and phonons, and what are phonons? Just quickly to remind you. Okay, so phonons are deformations of lattice. So if previously we discussed an ideal lattice and electrons as a Bloch waves in this lattice, that now we remind ourselves that actually lattice is not just a periodic potential. Lattice is built of atoms, and these atoms can move. The deformation of this lattice, and these deformations are called phonons. And obviously there is an interaction between electrons and phonons, and this gives rise to many interesting effects. In particular, we will be once again thinking about conductivity. Okay, so So let's draw some picture. So we had crystal. It was a periodic structure, and it gave rise to some periodic potential VFR. And we solve Schrödinger equation in the presence of this potential. And these were Bloch waves. But what happens if atoms of the crystals are being shifted from the equilibrium position? So we are supposed to think about a deformation where atoms of the crystals are shifted. So in particular, it can be that they are moved in some regular way. So then schematically we have regions of crystal where there's one periodicity of crystal, and then there's a region of crystal with another periodicity. And therefore, you can no longer talk about a unique Bloch wave that is valid for the entire crystal. And now, I don't know to what extent you're familiar with Phonon crystals, but there are several ways to create phonons in the crystal that depend on the unit cell of the crystal, how many atoms are in the unit cell. So there are always acoustic phonons, something which is associated with the deformation of the density of the crystal, and it's always there. But also, if the unit cell is more complex, if there are several atoms in the unit cell, there are additional optical phonons. So in principle, there are many phonons that may exist in the crystal, many types of phonons, and many types of deformation that give rise to effective interaction between crystal degrees of freedom and electrons that occupy the same crystal. And if you will look in the book by Gantmacher and Levinson, you will see the full zoo of different scattering mechanisms, the different types of interaction between electrons and phonons that might arise there. So in principle, it's not a universal, there's no a universal Hamiltonian that describes electrons and phonon interaction. It depends on the type of the material, on the symmetries of the material, on how many atoms there are in the unit cell and so forth. So without losing the generality, let me focus on the simplest possible situation of electron phonon kinetics and discuss the simplest model, which is called the model of deformation potential. So the logic, so we all understand that we are aiming at Boltzmann equation. So we now have two types of objects, electrons and phonons. So we will have to deal with two distribution functions: distribution function of electrons and distribution function of phonons. Two types of particles. Okay, so there are two types of particles, electrons and phonons, and we'll be interested in their kinetics, and there are large variety of possible equations. So we will be dealing and discussing it on the level of Boltzmann equation. So once again, let's write Boltzmann equation for electrons. V grad RF plus force, well, force including all the fields, and at grad P F is equal to the collision integral that involves now two types of distribution function. One is electronic distribution function, and another one is a Phonon distribution function. So strictly speaking, and in most general situation, we need to write another kinetic equation, and another kinetic equation will be for phonons. So we, strictly speaking, need to write also equation for phonons. Grad Rn plus force detects on phonons.
This is just writing again the Boltzmann equation, right?
Yes, yeah, but I'm want to stress electron phonon that now there are two Boltzmann equations because we have two types of excitation in the program. One type of excitation are electrons that we're already used to, and another type of excitations are called phonons, and these are eigenmodes of the crystal. Okay, so let us remind us what we know about phonons, and then we'll discuss the mechanism of interaction between electrons and phonons, and then we'll discuss where this interaction is important and what for. Okay, so what do we know about phonons at equilibrium? And this is generally true that phonons have Bose-Einstein statistics. They are bosons, and their distribution function is equal to 1 over epsilon of exponent omega over t minus 1. I hope I wrote this one correctly. And if you want to write it as a function of momentum, then this is the function. So you have some spectrum of phonons. Omega is a function of Q. Then the spectrum looks typically like this if these are acoustic phonons. Phonons typically like this if these are optical phonons. And there may be several branches of these phonons if the unit cell is sufficiently rich. Now, these particles are bosons. So the distribution function at equilibrium is of Bose type. Now, these particles are not conserved, so their chemical potential is precisely 0. And this indicates that the number of phonons is not conserved. So you may have a process where you start with one phonon, and this phonon decays, I don't know, in 2 or 3 phonons. And this is perfectly legitimate interaction process, as opposed to electron, whose number is always conserved. So if you're working with electrons, you start with 2 electrons, you end up with 2 electrons. There is no division of electrons. Electrons are conserved and elementary particles. Phonons, the number of phonons is not conserved. And this is because phonons do not have a charge, do not carry a mass, and therefore there is no conservation law that guarantees their conservation. So that's why chemical potential of phonons is 0, and there is no phonon conservation. So this was just a reminder of what we know about phonons. Are we on the same page?
Yes.
Okay. So now we are taking system.
Just to clarify, what did you say about the statistics of the phonons?
This is of bosons. They are bosons.
So just the plus and minus 1 in the statistics.
At equilibrium, if we are at equilibrium, it means it's more than plus and minus 1. At equilibrium, it means that there is a plus or minus 1 in equilibrium distribution function. Out of equilibrium, it means that there is no Pauli blocking. Instead, there is Bose-like enhancement factors. So instead of number of particles minus 1, you will have number of particles plus 1 there. Yeah, we will get into that story today, but remember when we discussed collision integral of electrons, we always wrote Pauli blocking factors because no more than 1 electron can occupy the same state. Because electrons are fermions, so only 1 fermion can occupy the state. For bosons, it's no longer true. You can have as many bosons as you want in the same quantum mechanical state.
Okay.
Yeah. So that's, yeah, it's called Bose-Einstein condensation. You can have all bosons sitting in the same state, and that's perfectly fine. Good. So now we will be talking about phenomena when we have a crystal. We derive this crystal out of equilibrium, acting on electronic degrees of freedom or on phononic degrees of freedom, and these two types of degrees of freedom are coupled to each other. So we act on electrons, and they drag phonons, or we act on crystal on phonons, and they drag electrons. So various equations of that type. Okay, the simplest equation to ask, or the simplest starting point, if we continue logically from electric conductivity, is to assume that everything is at equilibrium, and we apply some weak electromagnetic field that acts on electrons and practically does not act on phonons. That's because phonons are electrically neutral, and therefore electric field does not interact with phonons, and so electric field acts directly on electrons. Electrons interact with phonons, but there is no direct influence of electromagnetic field on phonons, which means that in linear response conventional limit, for most of situation, we can assume that phonons are at equilibrium and state equilibrium. So there is no need to solve Boltzmann equation for phonons. We can just say that for many problems, the distribution of phonons remains at equilibrium. So phonons are distributed in accordance to Bose-Einstein distribution function. And therefore, there is no need to solve separate Boltzmann equation for phonons. That's not always the case. That's the most universal case, but that's at least sufficiently popular situation. And definitely a good starting point. So we assume that phonons are at equilibrium, but electrons are not at equilibrium. So we need to write and discuss this guy here on the right-hand side. So we need to discuss electron-phonon collision integral. So we need to construct electron-phonon collision integral similar to what we did previously when we discussed electron disorder collision integral. And just continue this line of thinking. When I wrote here electron-phonon, I completely disregarded everything we discussed before, namely electron disorder collision integral. So what it really means that actually in this equation, there is also electron disorder collision integral, and they act independently, and they should be, strictly speaking, be added together. But now, just as an abstraction, since we already studied what happens when there is electron disorder collision integral, let's imagine for a second that there is no such a thing like a static disorder, and see what phonons do, and then we can restore both types of collision and see how they how to combine them together. But in principle, they are if there are electrons, if there's disorder in phonons, there are two types of collision processes, and they should be added up independently as two collision integrals. One electron disorder collision integral and another one electron phonon collision integral. So now let's look at the electron phonon collision integral and try to construct electron phonon collision integral. Okay, so what we know about electron phonon collision integral? Let me draw a schematic diagram that describes electron phonon collision. So we have electron at some state K. This electron interacts with phonons and emits phonons with the momentum Q. And electron goes into the state K prime equal to K minus Q. This is a process of phonon emission. Similarly, we can draw process of phonon absorption. So we have electron in the state K. Here comes phonon with the momentum Q. And electron goes into the state K prime equal to K plus Q. And this is the process of electron phonon absorption. Now, how are we gonna use this thing to construct collision integral? We need to write or postulate the probability of going from state K to state K prime by emission or absorption of the phonon. So let me write two probabilities, probability which I called W plus Q and probability which I call W minus Q. W plus Q will correspond to this process and W minus Q will correspond to another process. And I'll explain why there is a difference between these two processes. It looks very similar to the construction of probabilities of scattering from static disorder. And if I'm thinking in terms of Fermi golden rule, I need to write that this is 2 pi over h. Matrix element of the transition between states K prime with the emission or absorption of phonon square times, and here comes an important thing, a probability to have phonons with this momentum and energy conservation law, epsilon k minus epsilon k prime minus plus h omega q. So this is Fermi golden rule for the electron phonon scattering via absorption and emission. So this, the last object, last delta function is energy conservation. The first thing here is a matrix element for this process in the power 2. And the only non-trivial object here is this guy in the bracket. And this thing was absent when we discussed electron disorder scattering, because there was no such a thing if there is or there is no impurity potential. Impurity potential was there. Okay, it was there, but it was just a concentration of impurities, if you want. It was a total concentration of impurities. Here,
just a technical thing, why do you use H on the left and H bar on the right?
where do I do such a crime? Here. Okay. So here don't ask too many questions. I seriously hope that when you convert frequency to energy, you probably should be using H bar. Is this correct? So that's one thing, how you convert frequency to energy. And probably use H bar there.
I don't mind which do you use, and I assume it's correct. I just don't understand why there is both H bar and H in the same formula. Usually you choose a notation.
Okay, I might be sloppy with this notation. I could have just misspelled one of them. So there are two things. One is the conversion of frequency to energy, and another object is what you need to put in the Fermi golden rule. To my recollection, this is the correct one, but once again, don't treat this H bar and H2 series. I can check it, or we can look at it in any textbook and see what is the right way to do it. But that's, I hope.
Okay.
But that's really a minor thing here. What is more important is what stays in these brackets, and this is the probability to have this Phonon scattering. Yeah. So now look what is written here. So there are two processes. So there are these brackets, and for the let me just zoom into this bracket. So what is written here is that for the process with for W plus, for the plus process, it will be N Q plus 1. So this is for plus process. And for the minus process, this will be NQ. So what it means that imagine that you are at zero temperature. If you're at zero temperature, if crystal is at zero temperature, so if temperature is 0, that number of phonons is identically equal to 0. There are no phonons in the crystal. Therefore, the probability to absorb phonon from the crystal is 0. The probability to emit phonon with the momentum Q remains finite. So there is a distinction between two processes, the probability to absorb and probability to emit. Now, in order to absorb the phonon, you need to have phonons in the system. And if temperature is 0, there are none. As opposed to probability to emit phonon, which you can do anyway, even if there are no phonons in the system. Therefore, there is difference between emission and absorption processes. And this is differences precisely N and N plus 1. So there are two different probabilities. One probability for the scattering of electrons with phonon absorption, and another is probability of scattering of electrons with phonon emission. And there is some matrix element, and we'll come to this matrix element later. So now let's assume that we know that there are two scattering probabilities, one for emission, one for absorption. Then we can postulate the electron phonon collision integral that depends on two distribution functions of electrons and phonons. And this is equal to sum over all states k prime. K will be referring to electronic momentum, and to Q, which is the momentum of phonons. And here we go. There is a probability of phonon absorption, I guess, quote, from state K to state K prime, Fk 1 minus Fk prime times N. Yes, absorption. We need to have a phonon minus its partner, which will be emission, K to K prime, Fk 1 minus Fk prime. Sorry, I'm wrong. In these notations, sorry, like this. These factors are already included in W, sorry. What I wanted to say that this W minus is proportional to N and W plus is proportional to 1 plus N, but this building block is already inside W. Plus W plus and the momentum Q from K prime to K, F K prime 1 minus Fk. And this is emission, so it means that this process is proportional to 1 plus N, and plus W minus Q from K prime to K, Fk prime 1 minus Fk, and this is absorption, so this process is proportional to NQ. So this is almost satisfactory. The one thing which is missing in this story is what is M? What is the matrix element of the process? And this is the only thing that depends on the microscopic type of electron phonon interaction. So the construction in general is absolutely general, but now depending on the type of electron phonon interaction, whether it's piezoelectric or deformation potential or you name it, there are many names, this matrix element will have different types. And we will focus on the simplest type of electron phonon interaction, which is called deformation potential model. And this thing tells you that this object is just proportional to the delta function, which is this is just a momentum conservation, must be there for all types of things, times B of Q divided by the volume of the crystal. And B of Q.
Can you go up a little bit, please?
And B of Q will be just some constant that knows about microscopic of the crystals times the absolute value of the momentum. So when Q goes to 0, the interaction between electrons and phonons disappear. And if you really want to know what is B0, then B0 is H bar, I hope it's H bar, times something which called interaction potential constant divided by 2 rho and S, where rho is density of the material, S is sound velocity, and this thing is in deformation potential constant. So there's absolutely no way to compute it, but there are ways to measure it. So there are materials, there are tables of deformation potential constants in different materials. You can, if you are dealing with particular material, you can extract the deformation potential constant in this material. You have density of this material, sound velocity in this material. So if you know everything about the material, you know this constant B0, and this fully defines electron-phonon interaction within deformation potential model. Once again, this is not the only type of electron-phonon interaction, but this type of interaction always exists, regardless of what is the symmetry of the system. All other types of interaction may require some additional symmetries and additional richness of the unit cell. But for purposes, namely constructing most simple, understanding simplest properties of electron-phonon collision integral, this model is good enough. Okay, so now we know everything. We can plug this thing into the collision integral. So then electron-phonon collision integral looks like sum over K prime and Q, B of Q divided by the volume. And here will be a collection of terms, minus delta K prime minus K. I'll write it down, F of K, 1 minus F of K prime, NQ times delta function for energy conservation, epsilon K minus epsilon K prime plus H bar omega Q minus delta function K prime minus K minus Q Fk 1 minus Fk prime 1 plus NQ delta function epsilon K minus epsilon K prime. Okay, I will stop writing H bar. Let's set H bar equal H equal 1. Sorry for sloppiness, but let's assume they will restore them if needed in final formulas. Minus Q Fk prime 1 minus Fk 1 plus NQ delta function epsilon K minus epsilon K prime, sorry, minus epsilon K minus omega Q plus delta function K minus K prime Q F of K prime 1 minus Fk NQ delta function epsilon K prime minus epsilon K plus omega Q. So what I did here, I just substituted in the expression I wrote before for general emission and absorption processes, explicit expressions. And now I have a bunch of delta function for the momentum, but I have summation with respect to two momentum, fermionic and bosonic. So let me sum over K prime and eat one of the delta functions. So after getting rid of the momentum conservation delta function, I'm end up with an integral over bosonic momentum B of Q, and here will be terms minus Fk, 1 minus Fk plus Q, delta function epsilon K minus epsilon K plus Q plus omega Q, minus Fk, 1 minus Fk minus Q, 1 plus N, I forgot N in the expression above, NQ comes here, 1 plus NQ, delta epsilon K minus Q minus omega Q, plus Fk plus Q, 1 minus Fk, 1 plus NQ, delta function epsilon K plus Q minus epsilon K minus omega Q, and the last one plus Fk minus Q, 1 minus Fk, NQ, delta epsilon K minus Q minus epsilon K plus omega Q. Now notice that general structure there electrons are fermions. That's why they always go with a Pauli blocking. So we have always terms like F times 1 minus F, because you go from one fermionic state to another fermionic state. So the initial state needs to be filled and the outgoing state must be empty. Phonons, on the other hand, never get Pauli blocking terms. They always have enhancement, Bose-Einstein enhancement. So they either N or 1 plus N terms that come with N describe absorption. They vanish at 0 temperature. Processes that describe emission, they terms that are coming with 1 plus N, they survive at 0 temperature. They describe a process where electron loses its energy to phonons, excites phonons, and goes down in energy. Such processes exist even temperature of the crystal is 0. And delta function represent the conservation of energy for this set of processes. So if we combine all these terms together, we get integral over dq. This is d-dimensional integral, b of q. And here, okay, so let us write emission. Emission processes, they have a structure f of k, 1 minus f k minus q, 1 plus nq. These guys are emission plus, let me write on the next slide, fk minus q, 1 minus fk nq. These guys came from absorption. Sorry. Yes, correctly. Delta epsilon k minus q minus omega q. And plus, so these are emission. Emission, like these are absorption. And plus similar will be similar thing, minus f of k, 1 minus f of k plus q, n of q, plus f of q plus q, 1 minus fk, 1 plus nq, delta function epsilon k minus epsilon k plus q plus omega q. the end. So it's rather complicated. It's rather complicated collision integral. The entire specifics of electron-phonon interaction model, the details of interaction are encoded in this function B of Q. You give me the material, and I give you this function. Now let us try to understand the features of these collision integrals. And before we even start, let us discuss why do we need this collision integral? Why do we need to incorporate electron-phonon scattering into the model? Why we cannot always neglect it? And what is the difference between electron-phonon collisions and electron disorder collisions? What is the key difference between scattering, between electron and scattering in static disorder and electrons and phonons? Why these two things are conceptually different?
The bosonic nature of the phonons, maybe?
Yes, but how it affects what would be the manifestation? What would be the features of what is the physical effects that arise due to electron phonon scattering that are absent? What is this scattering? What is this is a scattering process, that is a scattering process. Here you go from state K to state K prime, and there you go from state K to state K prime. Why can't you think about electron phonon scattering just as another type of impurity? Yeah?
Because you have the amplification. As you have more boson, as you have more phonons, you're more likely to absorb, to emit phonons.
And when do you have more? Okay, good. And when do you have more bosons? How do you know you have more bosons or less bosons? That's a correct way of thinking. But how do you know when there are fewer bosons or more bosons? What controls this? What controls this? Temperature, correct. So as opposed to impurities whose number is fixed once and for all, number of phonons is essentially controlled by temperature. So therefore, electron-phonon interaction will be significantly temperature dependent. That's the statement number one. But now, can you think about phonons as impurities whose number is just given by temperature? So suppose we understood that the higher temperature there is, the more phonons you have. So let us think about model when you have impurities and the density of impurities proportional to temperature. Is it all? Is it correct?
I don't think so, but I'm not sure I have a good reason why.
Try to find the reason why. Try to find the reason why. And the answer to this question is depends. There is a situation when you can precisely think about phonons in the way I suggested, and there are situations when you can't. Now, how do you know whether you can or cannot think about phonons as static impurities? What is the key feature of the scattering for the case of static impurities? There was one feature of static impurities that was absolutely fundamental and was always correct regardless of what are the impurities. Think about conservation laws. What conservation laws was satisfied in the process of electron impurity scattering? What was conserved there?
The number of particles.
The number of electrons.
Yes.
Is it conserved in the process of electron phonon scattering?
The number of electrons is conserved, but
Yes.
the number of phonons is not conserved.
But let's think about some phenomena which is totally determined by electrons. Let's think about electric conductivity. At the end of the day, electric conductivity is determined by electrons because phonons are electrically neutral.
Right.
Therefore, all what is interest to us is how efficient electronic momentum is given to the lattice, whether it's given via impurities or via phonons. It's less relevant. We only are interested in the rate of momentum relaxation. So if you multiply number of phonons, who cares? Yeah.
Yeah.
You only interested. You only have a device that measures the number of electrons, and the number of electrons is conserved because electrons are fundamental particles. You cannot divide electrons, at least at energy scales available to humans right now. Yeah. So let's treat electrons as fundamental particles that cannot be divided, and this is a sufficiently reasonable assumption, at least for condensed matter setups. So number of electrons is conserved. The same as for electron phonon and electron impurity scattering. What other conservation laws are there?
The conservation of momenta and energy.
So what is conserved and where?
Okay, in the disorder we have conservation of momenta because we give momenta to the disorder or take from it.
Mind you, we are not interested in total momentum. We are interested in the momentum of electrons. The momentum of the entire system
okay.
conserved.
So in the disorder, yeah. So for the disorder, we don't have conservation of the electron momentum. Yeah, it loses momentum.
Loses or gains or whatever. Yeah, it changes its momentum. What about energy?
Energy should remain the same, I think,
correct,
for the case of disorder.
And that's why it's called elastic scattering.
Yes.
Elastic means that the energy is conserved. Electron goes, scatters off impurity, scatters off the wall, and goes back with the same energy. Energy is not changed. So electron at each energy, epsilon k, remains at that energy. It doesn't go up or down in energy. So there's a conservation of energy of electrons in each and every scattering event.
Okay, and in the case of phonons, we don't have that.
And in the case of phonons, we don't have that. So this is the key fundamental difference that, generally speaking, in the case of electron-phonon interaction, the energy of electron is not conserved in the process of scattering. Of course, the total energy of the system of electron and phonon together is conserved. However, the energy of electrons is not conserved. So therefore, generally speaking, the electron-phonon scattering is inelastic. Energy is not conserved. You have electron that comes with energy epsilon k. You emit a phonon with energy omega q, and you go down in energy to the energy state epsilon k minus omega q. This is your new state. Electron lost its energy and emitted phonon, or gained energy and absorbed phonon. So this is the key fundamental difference between electron-phonon scattering and electron disorder scattering. Now, there are situations, and we will discuss these situations later, when the change of the momentum is much larger than the change of the energy. So effectively, the process looks like that you have an electron-phonon scattering, and the change of electron energy is parametrically small in some sense, very, very small. So in this case, there are cases when the change of energy in the process of scattering, which is epsilon k minus q, is much smaller than everything. We will define everything later. And therefore, scattering processes are effectively elastic or almost elastic. The change of, it's not a real conservation law anymore, but the change of energy is much smaller than the change of momentum. Yeah? Momentum changes, the direction of the momentum changes, but the energy changes is very small. And in these regimes, the scattering between electrons and phonons is essentially elastic. And therefore, electrons act exactly as you proposed. They act exactly as impurity, static impurity, whose number is governed by temperature. So in the regime where scattering between electrons and phonons is quasi-elastic, that's the scientific name for it, when it's quasi-elastic, phonons are essentially acting as static impurity with their number controlled by temperature. This is the regime where scattering between electrons and phonons is very similar to the scattering of electrons and static disorder. But in all other regimes, and generally speaking, in other regime, scattering is not elastic, and energy changes in the process of this scattering. So therefore, electron disorder scattering only allows for momentum relaxation, because momentum is the only microscopic variable which is not conserved in the process of this scattering. Electron phonon scattering does not conserve anything but the number of electrons. So all other quantities can be equilibrated. Do we agree on that?
Yes.
Okay, good. So let us try to compute things. So let us compute a lifetime of electron let's assume that we have our Fermi surface. We have created electron in some state K. And we want to know how long it will take for this electron to leave the state K. So let's compute 1 over tau K, the typical rate of relaxation of this electron. And I just define it as a integral over dq, b of q. I'm just taking the whole collision integral I looked above, and okay, I'll explain better what I did. Just a second, let me write it down. I'm now trying to understand the scales, the typical scales in the system. So I'm looking at this collision integral, and I'm saying, okay, so it's a complicated object. I don't know how to analyze it, and it also depends on the problem. Let me just get some idea. What are the typical time scales in this problem? So let us assume that all electrons are at equilibrium. They populate the Fermi sphere at the temperature T. And now what I'm doing, I'm taking one electron and adding it to the system, saying now the distribution of electrons is Fermi-Dirac plus one electron that I place at the state K. That's my original distribution. And everything else is totally thermal equilibrium. So the distribution function here is Fermi-Dirac, and is Bose-Einstein. And I'm just looking at this thing and see what is outgoing current, what is outgoing current, I have in the collision integral. So essentially, I just decided to evaluate a single term in this complicated, very complicated object. I'm saying, let me assume that my f of k is just delta function. So, oops. Let me assume that this is delta function k minus k, I don't know, star, and compute this thing for k equal k star. So this will be k star. This is typically the typical time it will take for this excitation to relax as a result of electron-phonon interaction. Okay, so now let me forget star and just decide that that's going to be k. So, and then I keep writing and saying, let's think that spectrum of electrons is somewhat linear near Fermi surface, k minus k Fermi, omega q acoustic bosons, acoustic phonons, then delta function that stays here. It's delta function of V Fermi k minus k Fermi minus V Fermi k minus q minus k Fermi minus SQ, which is equal to delta function V Fermi k minus V Fermi k minus q minus SQ, which is equal to 1 over V Fermi delta function k minus delta function k minus q minus S over V Fermi times q. Now let us analyze something simple. Let's assume the temperatures are high. What do I mean by high? Temperature is much larger than omega d bar. What is omega d bar? If I go back to the page 1, no, sorry, too far. Here, that's my spectrum of phonons. This is the momentum Q. Somewhere here, there's a maximum momentum, which is 2 pi over the size of the unit cell. So this is the biggest momentum there is in the problem on the lattice. So this is the biggest momentum. So this is the biggest energy of acoustic phonons. And the claim is that this is omega d bar, the biggest energy accessible to acoustic phonons. So if I'm saying that my temperature is much bigger than omega d bar, what am I saying? I'm saying that if I'm in this regime, that n of q is essentially E omega q over t minus 1, but omega q is much smaller than temperature, because omega q is always smaller equal than omega d pi. So therefore I can expand this exponent, yeah? I can say that roughly speaking, it's 1 over 1 plus omega q divided by t. This is the exponent minus 1. Because omega q divided by temperature is something much smaller than 1. Then this thing cancel, and I'm getting that this thing is equal to t divided by omega q. So that's precisely the statement that we're already foreseeing, that in some regimes, the number of phonons will be linear in temperature, and they would act as impurities with temperature-dependent concentration. So now what can we say about Q, typical Q in this case? Well, we know that SQ will be omega d pi, which means that typical Q will be omega d y divided by S. Now, if you will estimate it parametrically and say that omega d pi is if you will, just a second, let me think if I need to say anything more. Just 1 sec. So it means that if I now look at the expression that I have in this delta function, yeah? So in this delta function, I now have a term. Let us look at the last term in this delta function. S V Fermi times Q. S divided by V Fermi times Q. So this will be of the order omega d pi divided by V Fermi. Just 1 second. All right, yeah. So I claim is this term, the last term, the third term in the brackets, it's much smaller. Is much smaller than the first two terms. How do I see it? So what is the typical K of the electron? Yeah? So if you look at our problem, so there is a Fermi surface. There is electron somewhere near Fermi surface with the momentum K. And there is a scattering of this electron. And it goes there. Now, my claim is that let's imagine that the size of the Brillouin zone, 2 pi over A A being a number of unit cell. So this is a parametrically something which we can estimate as K Fermi. Well, I don't know if it's trivial or not. So we have a metal. That's the size of so we have some unit cell of the size A. Then typical K Fermi would be 2 pi over A. If the metal is, I don't know, half filled. So for typical metal, K Fermi is 2 pi over A. So it means that that typical Q, which is omega d pi times S, will be typically of the order of K Fermi. Which means that this term, the last term in the purple, will be K Fermi times S divided by V Fermi. S is the sound velocity, V Fermi is the velocity of fermions. Now, typical sound velocity and typical V Fermi. Do you remember what are the typical sound velocity and what are the typical Fermi velocity?
I don't.
Order of magnitude. Who is bigger, who is smaller? Who moves faster, electrons or phonons? Let's start with that.
I think Fermi velocity is much larger than sound velocity. So sound velocity, I think, is like okay, I don't remember exactly, but maybe the order smaller than Fermi velocity.
So you want meters per second or centimeters per second? That's centimeters per second. Let's write centimeters per second. So what? So Fermi velocity is typically 10 in the power 8 centimeters per second. And sound velocity is typically 10 in the power 6 centimeters per second. And this is not the material science. This is something which is very universal. There is a very fundamental reason for that. Yeah? There is a very fundamental reason why Fermi velocity divided by sound velocity is 100 roughly. Where's this difference is coming from? Why one of these velocities? I'm talking about typical velocities. Yes, I'm not talking about some specially prepared nano array where you create slow electrons. I'm talking about normal metal or semiconductor, yeah, old-fashioned metal or old-fashioned semiconductor. So why normal metal Fermi velocity is much bigger than the sound velocity?
Well, because electrons are much lighter than ions.
Correct, because electrons are much lighter. So it's essentially a ratio between mass of the electron over by the mass of the atom. Atoms have protons in them. They all like 1,000 times heavier. And this ratio between mass of electrons over the mass of atom is precisely the ratio that makes Fermi velocity 2 orders of magnitude bigger than. So it's essentially square root, if I remember correctly, don't take me. So this is the mass of the atom, square root of the mass of the electron. So mass of the proton is 10 to the power 4, heavier than the mass of the electron. So you have a square root of 10 to the power 4. And that's why this thing is always 100. This is called, by the way, Migdal parameter. So mass of the electron is 10 to the power 4 lighter than the mass of the atom. Therefore, the ratio of this velocity is parametrically large. And that's why when we look at here and look at this term, where was this term? Here. It has this factor S over V Fermi, and this is 10 to the power 2. So if typical momentum is K Fermi, if K typical is K Fermi, and typical Q is also K Fermi, so the change of the momentum is K Fermi, so the picture is that there is an electron here sitting on the Fermi surface, and it goes somewhere there, phi away on the Fermi surface. Then this term has a smallness of S over V Fermi, and therefore it can be neglected. So in this situation, what essentially stays inside delta function is almost energy conservation. So if you overlook the difference between energy, which is really small, then you say that this delta function essentially becomes energy conservation delta function as if these were static impurities. And then in this regime, we get that 1 over tau outgoing time is given by this integral. This is T omega Q, this what came from the distribution function of bosons, and delta function of epsilon K minus epsilon K minus Q. And now, now you see that you can take temperature out. This will be the integral, d-dimensional integral, some B of Q, 1 minus F K minus Q divided by omega Q, delta function, epsilon K minus epsilon K minus Q. So scattering looks as if it's elastic, and the number of impurities looks, they are proportional to T, to temperature. This is large angle scattering, so 1 over tau out is essentially to 1 over tau transport, momentum relaxation time, and it's proportional to temperature, which means that electric conductivity in this regime will be proportional to tau, will be proportional to the temperature in the power minus 1. So in other words, resistivity, if you'll measure resistivity as a function of temperature, resistivity will grow linear with temperature. So we know what to expect when temperature is much larger than omega d pi. We're expecting linear in temperature resistivity. Each collision gives rise to energy, to the momentum relaxation. Number of collisions is proportional to number of impurities. Phonons act as their impurities, and this is the resistivity as a function of temperature. Okay, so now let's discuss low temperatures. Low temperatures. Let's put low. They're low in the sense that by low, I mean the temperature is much smaller than omega d pi. I, of course, assume that system remains in normal state, no superconducting transition, no other transition, just normal electrons with a well-defined Fermi C. no surprises. So now energy conservation is trickier. So what it means that omega q, which is equal to qs, is equal to the difference of the electronic energy, which is roughly V times Q. Q is T over S, and this is now much smaller than K Fermi. What it means, that if we have an electron somewhere there at the state K, it scatters, it emits, absorbs whatever phonon, it goes to the state K, this was K, this is K plus Q, but Q is much smaller than K. So essentially, it goes there. So if we draw the angle theta of this process, the angle will be Q divided by K Fermi. Q is thermal momentum T over S K Fermi. And this is something much smaller than 1. So it's the change of the momentum of electrons is very small. So let's write it in bold. Small change of the momentum. What it means? It means that there is a scattering, but in each and every scattering, electron changes its momentum by tiny amount. Yeah, so electron goes, scatters by small angle, goes, scatters by a small angle again. So we have what is called small angle scattering. So if you remember when we talked about impurity, static impurity, there was a small angle scattering there as well. So in case the impurities are very soft, there's an electron that goes and scatters by a tiny amount. Goes and scatters by a tiny amount again. And this process is random. And if you remember, that was the reason why we had two scattering times. One was a 1 over tau elastic, which was something like integral over d theta w theta, and another was tau transport, integral over d theta w theta 1 minus cosine theta. And this was how frequent electrons scatter. Or time between scattering. Yeah, probably the better way to say time between scattering, typical time between scattering. And this time it takes for momentum to relax, to randomize, to forget its original value. And now if W of theta is picked at small angles, then these two objects are parametrically different. So if we remember the similarity, so that what happens here as well in the process of electron phonon scattering. We have something similar to the change of the electronic momentum is very small, so we will have something of this type, and I'll write you the result, and we will derive this result carefully, but I just announce it that in this case, the time will be a function of the energy of electron, and it will be some constant times energy of electrons measured from chemical potential divided by omega d by K Fermi S in the power 3. So this is the situation where the change, the scattering is absolutely inelastic, and we end up having this result. Okay. Any questions so far? Is everything absolutely clear, or at least sufficiently clear?
Sufficiently is a nice way of saying it, I think.
Okay. If anything sufficiently unclear, so but you can ask a question which points to the to things that
I'm good for now, so I might need to revisit the lecture a bit, but I think I'm good.
Okay, so let me keep announcing stuff. So let me announce. Let me announce you the big picture, the big picture, and just give me a second. I'll reply and say I'm busy, and then. Okay, I'm gonna announce the big picture, and then we will fill in the details. So how do we want to understand what's going on? So let's draw a phase diagram. So what are the typical momentum that we have in this problem? So we have electron somewhere. We have Fermi surface, we have chemical potential, we have state, and we have energy of electron. And now we also have a temperature in the problem. So now we are thinking about relaxation of the electron that is placed somewhere above Fermi surface. Its energy is E. You can call it EK. So determined by K, if we place the electron there, we know its energy, and we also know temperature. So let us think what types of processes are allowed. So to think about it, let me define two typical momentum. So let's call one momentum a thermal momentum. So thermal momentum is just temperature divided by sound velocity. This is thermal momentum of phonons. This is one relevant quantity. And another quantity which I want to define is energy momentum. So this is energy measured from chemical potential divided by sound velocity. So this is essentially how much energy I can convert to a phononic momentum and how much temperature I can convert to phonon momentum. I can extract phonons gaining energy from electrons. I can extract phonons from thermal phonons. So these are typical scales that accessible for phononic degrees of freedom in this program. And we will go into details and calculations. Don't worry if you don't understand it. So if I draw the axis of these two momentum, I can be in different situations. So let me draw on this axis K Fermi and K Fermi. So these are positions of K Fermi. And let us see what happens in this problem when I'm in different regimes on this axis. So if I go here in this part of phase diagram, that's the part we already discussed in details. It means that my temperatures are very high. So when temperatures are very high, we saw that Q thermal momentum saying something wrong. So when we saw that when temperature is very high, the typical momentum of the phonon was of the order of K Fermi. And number of phonons was proportional to temperature over omega Q and was much larger than 1. So temperatures are high means there are lots of phonons, and each scattering electron goes from one point of Fermi surface to absolutely different point of the Fermi surface. That's why the typical momentum that it passes to phonons is K Fermi. That's the scattering picture in this regime. So this is high temperature regime that we discussed. So this is this part of phase diagram. What is this part of phase diagram? What happens here? Here, it means that we take electron and place it high above Fermi surface. So we take electron with a large energy, much larger than temperature. So what it means that in this regime, temperature is essentially very small, 0. You can think about 0 temperature, which means that number of phonons there will be much smaller than 1. We can think that temperature is 0, energy is very large. Electrons will interact with phonons by emitting phonons rather than by absorbing them. What will be the typical momentum change? I claim, and we have not seen it yet, that it will be also of the order of K Fermi. And what happens here in this part of the phase diagram is more trickier. I'll just announce the results. By no means these things are obvious right now. I just announced them so you will see the picture in general. So here I'm claiming that the change of the momentum is typical change of thermal momentum, and it's much smaller than K Fermi. Number of phonons is roughly 1. Here, typical change of the momentum is energy momentum, number, and it's also much, much smaller than K Fermi. And number of phonons is also of the order of, sorry, a number of phonons, wrong. A number of phonons is much smaller than 1. So this is essentially a low temperature regime. Yeah, so temperature is very small, so number of phonons is very small. So this is the large picture of what would be typical electron phonon scattering at different energies and different temperatures look like. And now what we need to do next, and I think we better do it next time because it requires sufficiently long and careful calculation. We're gonna show how these things can be derived carefully and from the terms of collision integral, and we will see that this picture will give rise to different scattering times that has a corresponding scaling with energy, with temperature, and will give rise to several regimes of temperature-dependent conductivity and temperature-dependent resistivity that will all follow automatically from this model. I think it's a natural point to pause this discussion and to dwell into the details of all these computations next week. So do you have any, if you have any questions, comments, please ask.
What's the capital S in the expression of Q epsilon?
Say it again.
What's the meaning of capital S in the expression of Q epsilon?
S is the sound velocity.
So the capital S and it's the same with the small s.
Oh, sorry, yeah. So where this is small and capital, I thought they're all the same.
Okay.
Yeah, so this is sound velocity. Essentially, I'm comparing the energy. So SQ thermal, it's an energy which is compared to temperature, and SQ is an energy, is a momentum compared to energy measured from Fermi surface. So I'm converting energy into the momentum in according to the dispersion law of phonons, but I have two possible energies that I might need to convert. One energy in this problem is the energy of electron, which sits somewhere above Fermi surface, and another energy scale, which is in this problem, is temperature. And depending what scales is bigger, I excite different phonons.
Okay, thank you.
Mm-hmm. Any more questions? There's something there in the chat. I think I left. Okay. So I guess that's it then. So see you next weekend. And goodbye.
Bye.
Please
Thank you very much.
remember to upload the second part of the second lecture.
If I'll find it, I'll upload.
Thank you.
I'll upload.
Thank you.
Mm-hmm.